Well, hello viewers. In this video, we are going to implement a solution to the real life problem of railroad crossing and gates operation using Edison robots and Legos. The agenda for this video is first the project overview to see what we are doing in this project, what goal we are trying to achieve, prerequisites required before you can undertake this project, material required to build it and put it together to create a working demonstration. Then we will look at a working demonstration of the project that I put together. And finally, we will do a code and a logic review of how the Edison robots are programmed to achieve this target. So in this project, an Edison robot representing a train will run on a track, and the track will cross over the black lines which will represent the roads. The roads are used by two other Edison robots, so hence there is a chance that trains and the cars can collide with one another. So to avoid collision between the cars and the train, two additional Edison robots will be used to represent gates, and they will close the gates to prevent the cars going over the track and colliding with the train. This is an advanced project. The difficulty is high due to the coding requirement and the mechanical setup required to make this project and do a demonstration for this correspondingly. It could take two or more sessions for a class size of 6 to 10 students to accomplish. I believe the age limitation should be 12 plus because of the difficulty and how advanced this project is. For the prerequisite, it's good if the students know A, this scripting in Python, that is how to do Python programming, and the ability to program Edison robot using that Python, have some experience in that. From the Edison robot side, the infrared communication, obstacle detection, and line tracking will be the three features of the Edison robot that we will use. So it's good if the students are familiar with that and how to enable and uh, use those features. Then some computer science concepts of state management we will discuss, because these robots will maintain states and will respond to the sensors and parameters and outside inputs accordingly. And finally, we'll need a creative approach from the students, because you can do different variations on it and try to solve this problem creatively the way you think that you can. So for the material, you need about 6 to 8 Edison robots. There's a white project board that you will need on which the Edison robots will perform this demonstration. So in the track, there will be a track that you need to draw using the black lines that will represent the road, and then the steel wire that will connect between two heavy objects that will represent the train track on which the train robot will run. Some Lego blocks, as mentioned before, and some miscellaneous items like tape and cardboard to put all of these things together. All right, this diagram represents the setup for the project. We have close to like 8 robots participating in this project. This one here represents a train robot, and this goes back and forth between the two terminals. The two terminals are just heavy objects placed at the end of the whiteboard, and they are connected by a steel wire. So this black line is not a black line, but it's a steel wire between those connected between those two heavy objects, and it goes through the Lego pieces attached on top of this robot. That will make sure that this robot does not just wander off anywhere onto the side and stays on the track all the time. So this represents your train and is just going back and forth. These two robots, the one that you see here and here, represents the car, which are going over a black line. So they will follow the line tracking algorithm. So the idea is when they are going over the line and the train starts coming in, they don't run into one another. So in order to do that, these two robots represents the gate, and they will close the gate when the train starts coming in, and they will open the gate when the train has left this road and is on its track on the way to the terminal. In order to make that happen, these two robots that you see over here are the sensors. They will sense the train coming in, send a signal to the gate. The gates will come down, prevent these cars, robots to go onto the road and onto the train track and collide with the train until the train has passed. That's when they get another signal, these gates, and these gates will open and allowing the cars to continue their journey on the road.
Alright, everyone, here you see the 8 robots that will participate in this program. You see 7 of them on the board, and one is in my hand, which is the controller that I'll be using to control some of the operations. What you have here is the main train representation by the robot. As you can see, it has some Lego pieces attached to it, and this is to make sure that the train stays on the track. And this metal wire over here is tied down to the end of the board via heavy objects so that the train does not wander off anywhere to the side. The reason why I'm using this metal wire and these Lego pieces, because I could not use the line tracking algorithm, as the train needs to cross over the black line, go to the end, and then come all the way back. This line tracking is going to be used by these 2 robots, which represents the cars which are going over the track. Now the track crosses over the railway line, and that's the whole purpose of the program, that the cars and the train do not run into one another. So in order to do that, these two are the gates that will close or open based on whether the train is approaching or not. To get that information, there are these 2 sensors, one over here and one over there, that will tell the gates through infrared signals that the train is coming or the train has left. When the gates sense that the train is coming, they will close the gates. When these robots will sense that the train has left and it is over the track, they will open the gates again and allowing these cars to go through. So this is a standard line tracking algorithm with object detection to stop it when they see an object, essentially in this case the gate. The controller that I am using, I'm going to use it to permanently close the gates. Suppose representing like a maintenance work going on, so that the gates won't open until I give the resume or the release command so that they start operating again. So it's like a force closure of the gates whether the train is approaching or not, so the cars cannot go over the track. Okay, so I have turned on the robots, but before I start running the program, I wanted to show you how the gates have been constructed. They are just simply using Lego pieces that are attached to the wheel of the robot. Both the gates are using the same program, and they respond to infrared signals received from the sensors, and they will open or close the gate as the train is approaching or the train has left. And in the end, you will see I have just attached some cardboard, light cardboard for object detection. Otherwise, if I attach too many Lego pieces, it becomes really heavy for the robot to lift up, and it's unable to do so with its motor. So the power is very low for these motors to be able to lift heavy. Now I have turned on the robots and moved them around a little bit. So the first thing I'm going to do is run the train robot, and it tracks this metal wire, as I said, using these Lego pieces. It keeps it on track, it doesn't let it go astray. So let's turn on the train. Something that I had to move around was this sensors that sense train coming in towards the track or leaving the track coming in towards the train terminals on either end. The second thing I'm going to do is turn on the gates, but the gates won't do anything because the sensors tracking the train are turned off. So let me turn on the sensors now. So this was a sensor to close the gates, but because they are already closed, they're not going to open. Now let's turn on the cars. The cars on the track are not going to run until the gates open and allowing the cars to go through. Okay, let me turn on this sensor as well. This is the one that's going to now give the signal that the train has left the track and it is now arrived at the station, so gates can open and cars can continue. Okay. All right, so the cars are running on the track, and when the train starts coming in backward again, this sensor again tells the gates to close. The way these sensors are working is that they detect whether the right uh, sensor is detecting a train and then the left, or the left sensor detects first and then the right. So that's how they know that the train is coming towards the track and has left the station, or it has left the track and has arrived at the station. That signal tells the gates to either open or close. Now, these robots which are tracking on the black line have a collision detection that prevents them from running into the gates.
Well, viewers, it's now time for the code review. The first Edison robot for which we are going to check the logic is the train robot. This robot is running fairly independently of any other robot, and you can just run it on its own. It has a metal wire that goes through the Lego pieces attached on top of it that prevents the robot from running to the left or the right, and pretty much it stays on track and goes back and forth between these two heavy objects. And that's it. It's not communicating with any other robot. So in the code side, what it has is direction. So this basically tells whether the robot needs to go forward or the robot needs to go backward. So initially we're going to start with forward, and there's a countdown. And the reason for introducing this countdown is to slow down the robot a little bit. So in this while true forever loop, the robot will check after every 70 milliseconds this code will execute, and it will check if the countdown has expired. Then it stops the robot, waits for 50 milliseconds, again enable a 70 millisecond countdown. Okay, so that's all this thing pretty much does. So it slows down, and your robot basically moves in jerks instead of going on a speed of one, because I still found the speed of one to be too fast. And even with this speed, the robot very quickly reaches the tracks and does not give enough time for the gates to come down, and which could result in the train robot running into the other cars on the track, on the road, right? So it's not a good way to model it. So you may in your program would have to consider things like these. Now, what happens afterwards, if how do we know that the robot has reached the end, is we are checking the drive stream. And the reason why we are checking the stream, we cannot do the object detection because this robot is going back and forth, so it can detect the objects in front, it cannot detect the object at the back. So the only way to know whether you have reached the end is to check the strain. If there's a strain on the motor, if there's no strain, then if it is going forward, keeps going forward. Otherwise, it goes backward, which means direction is one. So direction is switching between 0 and 1. 0 is forward, 1 is back. Now, however, if it is driving a train, it stops the train. It waits for 8 seconds. So now it means that the train is waiting at the terminal. And if the direction is 1, which means 0 means it was going forward, now set it to 1 and start driving backward. Otherwise, if the direction was 1, now set it to 0 and start driving forward. So that's how we know. The train has reached the end of the track. Now it needs to reverse its direction. Now, one more thing we're going to look at, and this is where the state diagrams come in, is what is the state of the train? So, going forward, going backward, stop at the front terminal, stop at the back terminal. So, if it is going forward, drives under its train, and then it basically stops at the front terminal. That's where it switches the direction, waits for the time expired, then it starts going backward. Then when it's again driving under a strain, then it means it needs to stop at the back terminal, and again it will wait for the time expire and start going forward. So that's the state transition diagram for the train. So now see how the cars on the track, basically these cars and that you see over here, these one and the second one, they are going round and round on this black line. Of course, they are following the black line line tracking algorithm, and this metal wire goes on top of it, so they are able to pass underneath that metal wire and are not affected by the train track. And the train is not affected by this black line because it's not using the line tracking. So on the car side, again, just like train, you can run these cars independently, but if you don't have gates and sensors, the train and the cars are ultimately going to run into one another. So one of the things that cars are doing is that they have an obstacle detection, and this is used so that if there are two or three cars on the track, they don't run into one another. Also, if you have the gate that came down and it is now telling the car that there is no access to the road, the cars use that obstacle detection to not continue further. And then on top of it, we also have the line tracker LED. So this is just a variation on the line tracking algorithm. Here we have the while true forever loop. If the obstacle detection is none, if there's no obstacle that has been detected, then again then it follows just the line tracking. If it is on the white, then if it is on the white, then drive a little bit towards the right. If it is not on the white line, it's on the black line, then drive a little bit towards the left. However, if you found that it is there is an obstacle in the left, right, or front anywhere, that it is this is not true, it is not equal to none, then it is there is an obstacle, it will stop and it will wait for 1 second. So this is just 1 second is just to give it enough time for the obstacle detection to read the obstacle and see if the obstacle has disappeared or not. You don't want to continuously keep reading it. It takes time for that obstacle register to refresh. This 1 second gives it time to get a new value, and when the gate is lifted, the cars know that they can proceed further. There is no obstacle in front of them. Now, the next code review we are going to do will be that of sensors. Sensors are actually quite complicated, and they are using both the left and the right obstacle detection to check whether the train is approaching towards the track, has left the station, or the train is coming from the track, has left the road, and it is now arriving at the station. So if you're going towards the roads and towards the track, and then you need to close the gates, let the cars know that there's train coming. On the other hand, if you detect that the train has just come over the roads and it is going on to the station, then you can open the gates again. And the way it's working is when the Edison robot detects that the train is coming from right to front, then it means that the train is coming towards the road, and these gates need to be shut. For this one also, if you see carefully, these additional sensors have been put on the opposite side of the track. It is the same program which is running in both of them. So when this one detects the train is coming from right to front, it's going towards the road. This one also detects the train is coming from right to front and it is coming towards the road. So you don't have to write two separate programs. Similarly, when the train is going from left to front, like the left sensor detects the train and then the front, detects that the train is here, means that the train is going away and has already crossed over the roads, and it is now safe to open the gates. Similarly, this one sensor also detects if the train detects that the train is first on the left and then on the front. It means that the train has crossed over the roads and the gates can be opened. So they then correspondingly give the signal to open the gates. And if the train is coming towards towards the road, they give the signal to close the gates. So let's look at the code. So you're maintaining so let's look at the state diagram first. So we maintain the states for this. So there's no obstacle, and if there's an obstacle detected at the right, which is here, then it goes into a certain state and it waits in that state for 3 seconds. And then after that, if it detects that there's an obstacle at the front, which means the train is going from right to front, then it sends close gate infrared message. Train is approaching, crossing, wait, 5 seconds. And after that, it waits 5 seconds to let the train pass so that it does not give any other signal for next 5 seconds and allow it to expire in that state. And then it basically goes back. Now, in this 3 seconds, the reason for this 3 second wait is sometimes you may incorrectly place an object or hand in front of it. You want this robot to go back to its original state. So after 3 seconds, it expires and goes back to no obstacle state if it does not detect any more obstacle. Same thing happens from right to front. If there's a train from right to front, which it means it's going towards the roads. Now, if it is left, which is detects the object first, then it also does the same thing. It puts it in a 3 second wait state. And then if it detects in front, then it sends a signal to open. So how it looks like on the board is that if the train is coming backward from left to front, this is the left side of the Edison, and if it detects here, and then it detects train in the front, it will send the open gate message, meaning, hey, the train has crossed the road, it's okay now, open the gates. Similarly, um, and then it will wait for expiration and it goes back to the no obstacle state, means there's no other obstacles around, everything is clear. So same thing for this one. If this uh, Edison robot detects the train at the left and then at the front, that means that the train is just leaving the tracks, the roads, crossing area, and it's going back towards the station. So it's safe to open the gates again. So let's look at the code, what the code looks like. So in this case, we turn on the obstacle detection. So that's the obstacle. Then there's a state being maintained by the what is the left obstacle and what's the right obstacle. What is the previous state of left and the previous state of right. And it's going to be used to maintain the state as we detect the object in the left and then the front or right and then it waits for 2 seconds. Then it reads obstacle detection, which is just to clear them. And that's the convention to clear them. And then I'm also using two strings to basically just generate separate auditory signals for me to know whether it is sending a infrared message for gate close or gate open. So it's just for myself to know. There is no need for that though. If you're quite confident with the code. Now in this forever loop, it keeps checking the obstacle state. And if it detects an obstacle, if it is a left obstacle detected, or if it is right. So if it is left detected, it will turn on the left LED. It starts the countdown. And again, as I said, within this countdown, if you are able to detect an obstacle at front, means that that there is movement and train is basically, in our case, has left the track, this one. Or if you detect the right one first and then you detect this one at up front, then the train is approaching the track and then close the gates. So that's how it's really working. So if the train is coming from the left, The left LED is on, the counter is started. Within 3 seconds, however, this thing fires and the previous obstacle is set to 1. So when the train goes up front, so now goes from, if I go back to the diagram, it goes from left to front, like comes here, the left one detects, and then the front, it's the train is detected at the front. What it does is says, hey, where was the previous? If the previous, did I detect a previous? Yeah, I was able to detect a previous left. And I'm going to turn off the obstacle detection. This is needed to send the eye infrared data. And I'm gonna send the auditory signal of play the tune of leaving that the train has left the railway crossing, so it's good. And we open the gates and again turn on the obstacle detection beam and wait for 5 seconds. So this just helps to for the train to have left and the sensor not to detect any more train that is obstacle and wait for 5 seconds and then clear the obstacle detector and then it resets the state. So what the reset state does is this function over here. It sets both the left and obstacle right obstacle variables to 0 and then turns off both the LEDs. So both the variables are set to 0, which means that the sensor is ready for another input. Similarly for the right, if an object is detected on the right, so in our case, if it is right and front, it means the train is approaching towards this railway crossing. Then start the counter and set the previous one that is I have just detected at the right. And if I detect it at the front, it checks what was the previous state? Did you detect it at the, just like at the left, did you detect it at the right? Yeah, we detected it at the right. So it means that the train has moved from right to front and it is going towards the railway crossing. So, so first we turn on the both LEDs, start the counter, right? It's kind of not really needed, but it's there, okay. So, and then it basically waits for like 5 seconds after it sends the signal for train is approaching to close the gate. Play the incoming tune that is the train is approaching and the gate needs to be closed. Again, turn on the obstacle detection that you just turned off and wait 5 seconds to for the train to clear. And then read the obstacle detection to clear the obstacle detection sensor. And this kind of is not really needed. I think we can remove it. Now at the bottom, you see it basically every under 10 millisecond it checks if the countdown has expired. So which is the one that we in both the cases we did over here and here. So for the left, when we detected obstacle at the left, and also when we detected the obstacle at the right. And the reason for resetting this is, as I said, if you accidentally place something here and remove it, or place something right or left and remove it, then you want the your Edison to go back to original state and does not just keep waiting for here's the train come front, has the train come in the front yet. No. So it gives a 3 second delay. And within 3 second delay, if the train has not basically come to the front, this 3 second delay, the train has not come to the front. It means that it was a incorrect reading and the state can be reset and and this countdown expires and it resets the state and you have both the LEDs turned off and both the previous variables that were maintaining the state of left and right obstacle reset to 0. Well, now we are going to look at the implementation for the Edison robot, which is controlling the gate. These Edison robots, this one and this one, are basically getting messages from the sensor robots here, which tells whether the train is approaching. the railway crossing or has cleared the railway crossing, and they correspondingly, when they receive that infrared message, they either open or close the gates. And when they close the gates, the cars cannot go over the black line, and they wait for the gates to open. And when they open the gates, the cars are able to go through this black line. So how does the code review looks like for that? So basically, it's really in the itself loop. It's not doing anything. It's just an infinite loop. It's just waiting for these infrared signals, and it responds to that. In addition to that, we have also basically configured the key round and the key triangle um, messages, the event messages, and this allows for debugging so that I can manually click these buttons and see whether press these buttons and see whether the Edison robot is able to open or close the gates. But in the live program, this infrared message received is the message that is going to do the job, is what you need to implement to open or close the gate. So when it receives the infrared message, and this is the infrared handler which is configured, it reads the data, and it depends on these two, 25 or 30. And what I'm using 45 and 54 is the manual controller, and I'll discuss that in a bit. So if you receive 25, it's meaning it needs to close. If you receive 30, it means it needs to open the gate. If you go back to the sensor um, program, you will see that for the case of train approaching the track, it sends IR data 25 to close the gate and open the gates if the train has basically left the track or the railway crossing. So 30 to open and 25 to close. So when you receive 25, then it basically closes the gate, and this is what the close gate program does. It detects the obstacle detection beam. It turns it on, and this is the one that the Edison is going to use to detect whether the gate has come all the way down, and it will stop. Otherwise, it will keep going down. So it's going to use that. So you need to enable that. Then you need to read it to clear that sensor. Wait for 200 milliseconds, give it some time, and then in the while loop, you're going to keep doing that. So what's doing in the while loop, it keeps checking the obstacle detection. If it is not, then it drives the left motor forward a little bit at the speed of 1, and then waits for 5 milliseconds. So it drives a little bit, waits for 5 milliseconds, right? That's how long it drives. Then it stops. Again, reads the obstacle detection. This is just to clear it. Waits for 300 milliseconds again, and then the loop goes back to over here. Okay, did I detect an obstacle? And if it is still not there, it keeps doing it, driving it a little bit forward for 5 milliseconds, then stop, clear the obstacle detector again, wait for 300 milliseconds for the obstacle detector to reset, then check it again. And finally, just close it to stop in case if it was moving. You don't need to, because okay, the last statement has to be stopped it. But then we change the current gate position to 2, means that the gate is closed. And we're going to use this in a bit. And ED obstacle detection beam is off. So we have to turn off this obstacle detection beam that we turn on over here so we can receive the infrared messages. Now, when you receive infrared data 30, which is open the gate, in this case, I'm not using the obstacle detection. Just basically drive it backward, the same left motor backward for um, for the speed of 1, or like I think like 2 seconds, 2 centimeter or so. What it does, it basically lifts the gate enough. So I just checked like which value is the best, and 2 made sense. It lifts the gate enough to allow the cars to basically go on the track. But before that, it checks if the current gate position is not equal to 1, which means if it is 2, and also checks the override. And this is I'm going to discuss in a bit. And that's the only time when it basically lifts the gate. If I don't check it, and if it receives the open gate multiple times, your left motor is gonna drive the gate all the way to the back. So it's gonna pretty much flip. So if the gate is over here, for example, left over here, it's gonna flip all the way to the back and can even, the Lego pieces can come off. So that's why I have to check. Only if it is not open, that it is not equal to one, it is then you attempt to open it and send and then set the gate position to one. So it's not gonna open it again if it is already open. For the close, you don't have to do it because it's detecting the obstacle and the obstacle is the gate itself. So the gate is in the front. It's not going to keep trying to close the gate because it's already providing the signal that no, the gate is already in the front. So there's already an obstacle in front. But for open, there is no obstacle. So I have to drive it to a small distance and then I have to remember its state to not open it again if I receive that signal of open again. So that's why it's preventing the left motor to keep, uh, you know, driving the gate up, 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 and back, and then the Lego pieces will come off. All right. Now, how? Let's look at the state diagram. So, state diagram for the gate is this. So you have a gate open, then you have closed gate signal received, the gate or closed gate override. We'll discuss override in a bit. Gate closing, keep doing it until an obstacle is detected, which means that the gate is in the front, and that's how the cardboard are doing their job. An obstacle, if there's any obstacle detected, the gate is closed. Then remain the gate is all the way down now, and we don't need to keep doing this again and again. So it's open, it's closed, and then in the middle state, which is when it is coming down. And then when it receives an open signal, then and then there's no override, then it basically opens the opens the gate. Now, what is the override for? So override is signal 45 and 50. These overrides are being sent by the controller. Let's see where it is. So this is the controller. It does itself does not do anything. It waits for. So this is in the hand of somebody who wants to manually close the gate permanently, and it sends two information. One is like 50 and one is 45. And 45 is gate close override is equal to 1. So the gate close override is so the current gate position when we start is 0 is closed and 1 is open, and gate override is 0, which means we haven't overridden the gate and it should behave normally. When you receive 45, which means we are overriding the behavior of the gate and closing the gate. So when you receive it 45, what it does, it closes the gate, which is this function. So it closes the gate if it is not already closed. Otherwise, the position will tell this object obstacle detection will tell that it's already closed. So it's not going to close further. It's not going to go down further. So you have to watch out for those conditions, right? And then it sets the gate close override equal to 1. What it means is that the gate is now in the close and it is the override has been set to 1, which means if I receive an open message, I'm going to check and override is equal to 0. So this one only works if the gate is not open, which means it's not 1, and because 1 is open, so 2 is closed. So if it is 2 and the gate override is equal to 0, which means the gate is behaving normally, then only it opens the gate. So the this sensor that you have over here, this control that we have over here, overrides to force the gate to be closed, and then it removes the override, but it does not open the gate. It just removes the override, and the gates over here wait for an open signal from the sensors before they can open it, because they don't know, maybe the train is already on the way, so they have to wait for an open signal, so they will not open the gate. So if this controller closes the gate forcefully but does not open the gate, it just removes the override for the gates to open. These Edison robots must receive an opens infrared message from these two sensors too. Correspondingly, after the override is removed, must receive uh, remove the open signal before the gates can be opened. All right, so that's the behavior of the whole um, manual controller, which you can also implement in addition to the basic railway control automated program.
Okay, so the one thing that we did not get a chance to test is the controller, which is in my hand over here. So I'm going to run the train again. What this controller will do is going to shut down the gates, and it will prevent the gate from opening when the train is has left the track and it is on the station. Suppose there's some kind of maintenance work that needs to be done and you want those gates to be permanently closed. So that's what the controller is for, is to manually control the gates and just close them and not open them even if the train has left the track. Let's first run the train. Now this will give the signal to the gates to open. The gates have opened and the two cars are going through. Now I can close the gates using my controller. And even though the sensor detected the train afterwards, but the gate had already been closed, so they are now not going to open even if the train reaches either end of this board and these sensors tell the gates to open the gates but they will still not open. So let's see. So now the train is reaching towards the end, and this is a signal to open the gates, but you see they did not open until the override for closing the gates that I have issued. I removed that override, so I'm gonna let it go through one more time. Now this is a signal to close the gates, but they are already closed, so they're not gonna close again. Now you will again see that sensor over there will tell the gates to open, but the gates will still not open. Let's move this. So you will see that sensor gave the signal to open, but the gates did not open. Now I'm going to give my override, which is by pressing the round button on my robot. So this gives the signal the gates can open. The last signal that it received from that sensor was to close the gates, but they're already closed. I'm not opening the gate. I'm closing the gate through my controller. Then I remove that override, but the gates will not open until they receive an open signal from either of these terminal sensors at the end. That is, the train has reached the terminal and has crossed over the track already. So now you'll see. So now when this robot gives the signal to open the gates, the cars on the track can start going and the gates are open again. And the cycle repeats itself, as you can see. When the train reaches that sensor, it's gonna again give the signal to open the gates, and the cars can continue. So that would be the end of the program.